Hey, here's another screencast. This one on a definite integral. And we're going to build off what we've talked about concerning the Riemann sum and define this really important idea in calculus called a definite integral. I will remind you the calculus has two parts to it. People like to talk about calculus as if it has two parts. It really has more. They talk about the definite, the differential calculus and the integral calculus. And here we go. We're starting to talk about the integral part of that. You've already seen the indefinite integral, which is another word for the antiderivative. This is a slightly different beast, but will be connected to the indefinite integral in the fundamental theorem of calculus when we talk about that. Last time I did this example, I think it was something like, what is the Riemann sum for f of x equals x squared plus 1 on the interval from -1 to 2 for n equals 9. And I think we came up with something like the sum as I goes from 1 to 9 of, what would it be, -1 plus I times a third squared plus 1 times 1/3. I think that's the Riemann sum we would write down for that, using the right endpoints of each of the subintervals. There was nothing special about the number 9. Okay. What would this look like if we just wanted to leave the number of rectangles open? So this here, we could define an area function and say this is the area approximation we get with 9 subintervals. What if I want to define a function a sub n that is the approximate area we get when using n rectangles? Can we do that? Yeah, absolutely we can do that. Well, let's go through this process again. So this is what the Riemann sum looks like. We've used this a bunch so far. Now, the number of rectangles were, in our previous examples, we were given, like this one, we were given a number for 9, a value for n. Here, I don't want to be given a value for n at the start. I want to leave that for the end. So we're going to let that be. So let's look at what these other things might be. What can I say? Well, I can say delta x is my interval, the length of my interval divided by n. So delta x is 3 over n. So as n gets bigger, that is, I get more and more rectangles, the width of the rectangles gets smaller. So this kind of checks out. My function is x squared plus 1. And how about these partition points? Well, these partition points are going to change with n. So it's always the case that one partition point is the previous partition point plus delta x. Now I can trace this all the way back to my leftmost partition point, -1. I can say this is -1 plus I times delta x. Well, this is going to be my expression for the ith partition point. Start at the leftmost endpoint and add I multiples of my widths. All right, so this is good. I think this is all we need. So we can write down our Riemann sum. I goes from 1 to n of f of xi. So that's f of -1 plus I times 3 over n times delta x, which is 3 over n. Now let's use our formula. So our formula is square the input and add 1. So there's our value of our function at the right endpoint times the width. So there we go. This is our expression for AN, the area we get if we use n rectangles. Now you can say, well, what do we get? What's this look like for a value of n? Well, you might turn to Wolfram Alpha. And Wolfram Alpha does an interesting thing. If you plug in this sum, if you say sum of all this as I goes from 1 to n, Wolfram Alpha is going to give you this funny expression back. It'll give you a formula for a sub n. It looks like this. And there's no sigma notation. Wolfram Alpha has done something to look at this pattern and see that it turns out to be this. So that's fine. Don't get excited about it. There's a theory of summations that we could talk about that would show you how to do exactly the same thing. But we don't need to do that. We'll let Wolfram Alpha do it. And this is really the important thing, because watch this. So if we multiply this out, we get n squared, minus 6n plus 9 all over n squared plus 1. Take this one more step. We get 1 minus 6 over n plus 9 over n squared plus 1, which is 3 times 2 minus 6n plus 9n squared. So this shows us something that's going to be important in a second. But going back to the problem, we have found right here, a formula for this function, an, that gives us the approximate area when we use n rectangles, the approximate area under this curve. Okay? This is perfectly good. Wolfram simplified it for us like this. This works perfectly well. So if I want to find the area with 9 rectangles, so A9, that's going to be 3 times 9 minus 3, which is 6, so 6 squared over 9 squared plus 1. And so what is that? 3 times, so how should I do this? That's 2 squared times 3 squared. This is 3 squared times 3 squared. Those cancel. If I multiply through by my 3, I'm going to get 4 thirds plus 3. Well, you get the picture. 13 thirds. That's going to be the approximate area when I use n equals 9 rectangles. What I want to point out to you is what this tells us. As n gets bigger and bigger, where is this number going? Well, as n gets bigger and bigger, this gets smaller and smaller. This gets smaller and smaller. And so, in fact, this goes to 0, and this goes to 0, and you end up with the number 6. And this is the exact area under the curve. So let me write that in a different way. AN is the Riemann sum. And that's approximately equal to the area under the curve. But something amazing happens. as you make these rectangles narrower and narrower, the area of the rectangles gets closer and closer to the area under the curve. That is, this left-hand side gets closer and closer to this right-hand side. And in fact, if we take the limit of both sides, right, the limit of the area under the curve is just going to be the area under the curve. But if I take the limit as n goes to infinity of an, which is the limit as n goes to infinity of this sum, this approximation becomes an equality. And taking this limit historically is called the method of exhaustion. Method of exhaustion. Think of it, how exhausting it would be to make more and more rectangles that are narrower. But what you're exhausting here is you're exhausting the area under the curve. You're exhausting the area. You're getting rid of it, okay, by taking a limit. So okay. Super important idea. Okay, that the area under the curve is the limit of Riemann sums. This thing here, this limit, as n goes to infinity of the Riemann sum in rectangles, is called a definite integral. Okay. And it's a lot to write. Lots of symbols here. So mathematicians have simplified this by taking this summation, the limit of the summation, and using an integral curve. It looks like an S, and that's why, because it comes from a sum. And then we put the endpoints here at the bottom and the top, kind of like the limits of summation here. We call these limits of integration. And then it's kind of using the notation for the indefinite integral. But this is called the definite integral of f of x on the interval from a to b. Okay. And the theory of the integral calculus is all about calculating these. Okay. Calculating these values. Calculating areas under the curve. If there's one thing I want you to be able to tell me a year from now when I ask you, hey, what do you remember from the calculus? I want you to say, hey, I remember the area of under the curve is the definite integral. I don't expect you to remember how to calculate it or remember that it's the definite integral is related to this thing. I expect you to remember this symbol and what this means. It means area under the curve. You'll see that when we calculate these definite integrals, although they're defined this way, there's a thing called the fundamental theorem of calculus that's going to give us a different way to calculate these that's much more straightforward. We're going to prefer it over using this because this is kind of gory. This is kind of hairy. So with that said, let's just play around and look at this for a second and get a feeling for what's happening here. And I'm going to go through two examples. So the first example is meant to convince you that indeed this is an area under a curve. And one good way to do that is start with a curve that you understand, and you can already calculate the area under the curve. That's a constant function. So I'm going to say f of x equals 2 on the interval from 1 to 7. So we want to write the definite integral for this. That's the limit as n goes to infinity of the sum as I goes from 1 to n of f of xi delta x. Well, what is that? Well, this is the Riemann sum for n intervals, n rectangles. So this limit statement doesn't change. The summation statement doesn't change. Okay, that's got to stay that way. I need to figure out what these are. Well, this is pretty simple in this case because f of xi, the value of my function at the right endpoint, well, is 2. It's 2 everywhere, so that's just a 2. And delta x here, well, it's the length of my interval over the number of subintervals. So the length of my interval here is 6. And that's 6 over n. So that's the definite integral. So we could stop there, but I want you to see something. So notice here with what's happening here. Well, I've got 12 over n, right? This simplifies to 12 over n. But 12 over n, that expression doesn't have an index in it. So this is constant. This is in every summation or every summand. And so one of the things we learn about sigma notation is that we can pull constants out. So this is the limit as n goes to infinity of 12 over n times the sum as I goes from 1 to n. But when we factor out a 12 over n, we're summing up ones. Well, what do you get when you sum up n ones? Well, you get n. So we've just simplified that summation out of existence, kind of like Wolfram Alpha did in the previous example. And here my n's cancel, I get 12, and the limit as n goes to infinity of 12 is just 12. So I just calculated this definite integral equals 12. And what's the area under my curve on the interval from 1 to 7? Well, it's the area of this rectangle. 2 high, 6 wide. The area is 12. And my Riemann, or my definite integral, really bears that out. It got the same answer. So the definite integral is giving you the area under a curve. Let's do another example. So we'll write the definite integral for f of x equals 3 times x minus 2 on the interval from 2 to 6. The definite integral is the limit as n goes to infinity of the sum as I goes from 1 to n of f of xi delta x. That's the definition of the definite integral. And so what we're going to do is figure out how to substitute, what do we substitute in here? So let's do some scratch work. What's delta x? Delta x is the length of my interval. Here it's going to be 4, 6 minus 2 over n, the number of rectangles, right? That's n here. So we get 4 over n. My xi are going to be, they're always xi minus 1 plus my delta x. But I can think of this in terms of my left endpoint, which is 2. And so I'm adding I copies of my delta x to get there. So that's the expression I'm going to use for xi. Is that it? Delta x, check. F, oh, I should do that f here. F of x equals 3 times x minus 2. And then xi, good. So let's rewrite that. Limit as n goes to infinity of the sum as I goes from 1 to n of f of xi. So we'll do that 3 times xi minus 2 times delta x, 4 over n. So continuing this down here. This is the limit as n goes to infinity. The sum as I goes from 1 to n. Okay, 3 times xi minus 2. So we're going to put in xi. Here's my xi. 3 times 2 plus I times 4 over n. Okay, xi minus 2. Oh, look, I can simplify that a little bit more because I got 2 minus that 2. Yeah, that's good. So the limit as n goes to infinity. Sum as I goes from 1 to n of 3 times I times 4 over n times 4 over n. Good. Good. So that's an expression for my definite integral. And that's how I would leave it. If I were asked to write a definite integral, that's how I would leave it. Let me just note, I'm going to note two things. The first thing I'm going to note is that this is the definition of this. So here's the symbolic representation of this. And if you looked at this, when we wrote this down, if you looked at this sum, you could see that this sum represents this definite integral. Because you've got this pattern 3, this looks like an xi minus 2, so you can kind of see that pattern there in the integrand. You can see out here everything's multiplied by my delta x. And then if you can see, this is the xi, so you can see that's the 2, that's the lower limit. And then you can say, well, here, if my delta x is 4 over n, or let me point here, 4 over n, and I've got n of those, then that gives me my right endpoint. Or that tells me the length of my interval, actually. And so this tells me my interval length of my interval is 4. So starting at 2, going up 4, takes me to 6. So there's a way you can look at the summation, this definite integral here, and decode it to see this. I just want to point that out to you. We won't really have to do that in this class, but it's there. The patterns are there for you to see and to use. But what's important for you to know is that if I give you this symbol means this. And being able to go from this to this is an important skill. So my second note is this. Let's look at this and let's take this a step further, because we can. Here I've got my index for my summation. And here I've got a 4 over n, and here's another 4 over n. And here's a 3. These 3 things are in every term, every summand. So I could factor them out. And factoring something out of a sum is like pulling it out of the summation symbol. So this is the same as this. I'm just working with the summation sign. So I could simplify this down. I've got a 16 times a 3, which is a 48. So I've got 48 over n squared. Now it turns out this has a nice formula. This always sums in a certain way. In fact, it always sums to n times n plus 1 over 2. You'll notice I just wrote this. It doesn't have a summation sign in it. So I'm doing kind of what Wolfram Alpha would do if you gave it this summation. It uses a fact in the theory of summations to eliminate the sum. But why is this useful to us? Well, look at this. So this is 24 times n plus 1 over n squared. This is n squared plus n. Let's write this one more time. If you work this out, you get 1 plus 1 over n. And as n goes to infinity, this 1 over n goes to 0. And so this whole expression goes to 24. So this shows that in this case, we could take this definite integral and evaluate it by hand, and we'll get the number 24. So look, my function here, the graph is a straight line. At 6, it goes to the point 6, 12. So I'm just calculating this region here, the region of a triangle. It's a triangle of width 4 and height 12. So we know from plane geometry that its area is 1/2 of 4 times 12. 4 times 12 is 48. That's 24. The definite integral bared that out. It gave us the same answer as the plane geometry formulas gave us. So hopefully this will help you understand and believe that indeed this definite integral thing, which is written right here, but this is the way we think about it, this is actually the area under a curve. And I'll stop there. I'll let you do some examples from the text, and I will see you next time.